Welcome to Definite Integrals, Definition and Properties. In this video, we will start off with the definite integral and talk about what it means as the area under a curve down to the x-axis, as well as revisit the old limit process that we did in the last video. Then we'll take a look at some of the different properties of definite integrals and figure out how we can find the area under certain curves using geometry and not calculus. Let's take a look at the definite integral. It is the area of a region under the curve. So let's let f be a function that is continuous and non-negative. Non-negative just means that it is either on the x-axis at 0 or it's above the x-axis in a positive, like positive y values. So long as f is continuous and non-negative, between a and b are lower and upper limits, then the area of the region bounded by the graph of f, so under it, bounded also by the x-axis, so that's like what it goes down to, and then our vertical lines x equals a and x equals b. So those are our lower and upper limits. So we're bounded by the curve, the x-axis, and a and b. Then the area of that region is defined as the definite integral from a to b of f of x dx. F of x is the function, dx is variable of integration, and then a and b, like I already said, are the lower and upper limits of integration. Sometimes these are also referred to the lower and upper bounds of integration. I have heard them referred to as both things. And then we have already defined this region using a much crazier looking definition that we called using the limit process. So we have already defined the definite integral from a to b of f of x dx as the limit as n approaches infinity of the sum from I equals 1 to n of all of those rectangles under the curve, and we wanted the number of rectangles to approach infinity. So we were taking the area of all these rectangles under our curve. And remember, to take the area of a rectangle, it was the height of the rectangle, which was f of c sub I, since that was the height, that is like where we're at on our curve, times the width or base length of each rectangle, which was delta x. And technically it's delta x sub I, just because it's whatever width we were taking at whatever x value. So this is technically the definition of the area underneath a curve, the definite integral from a to b. We kind of worked through this previously, and this is the long way to find the area under a curve. In this video, we will not necessarily find the short way just yet, evaluating the definite integral. However, we will see that there are much simpler ways to find the area under certain curves. Then finally, another theorem is that if f is continuous on the closed interval from a to b, so meaning there are no holes or gaps or asymptotes, anything like that, so long as f is continuous on the closed interval from a to b, then f is able to be integrated. And I have to confess that I am not going to say this word correctly, so I will say able to be integrated. So we're able to take the integral of f on that interval from a to b. So long as we have continuity, we can take the integral. Let's start off slow here, and let's just represent these two areas using a definite integral. So in part A, we can see that we have the curve f of x equals 4x minus x squared. It's given. So it is a quadratic. It forms a parabola that is opening down. We see that the shaded region in pink here goes from 0 to 4. Those are our lower and upper limits of integration. So the way that we can write this definite integral is that it is the definite integral from 0 to 4 of our function f of x, which is 4x minus x squared. Then our variable here is clearly x, so we'll write dx. Note, if this was like f of t equals 4t minus t squared, we would simply have t's here, and this would be dt. It means the same thing. So I put parentheses around this function because if we don't put parentheses around it, then it looks like the dx is only going to the x squared. When we have an integral and it has more than one term separated by a plus or minus, you do need to make sure that you put parentheses around it. So this is representing the area that is shaded here in pink, the area under our curve. In part B, we want to do the same thing. Except this time, our lower limit of integration is -1 and our upper limit is 1. We want to find the area underneath the curve down to the x-axis that's bounded between x equals -1 and x equals 1, these vertical lines here. The function is defined as 1 over x squared plus 1, so we'll write that in here. And this is not more than one term separated by a plus or minus. It is a quotient, so we do not need parentheses, and we'll put our dx there. So this expression right here, the integral from -1 to 1 of 1 over x squared plus 1 dx, represents the area underneath this curve here from -1 to 1. Here we're going to go the other way than what we just did in those two previous examples, and we actually have a definite integral. We have 4 of them. What we want to do is sketch the region that each one represents, and we want to see if we can evaluate them without using calculus. Hint, we are going to be able to evaluate 3 of them using geometry only. Let's sketch part A. We want the definite integral from 1 to 3 of the function just 4 dx. So this means that we want to sketch the function y equals 4, or f of x equals 4. Well, that is just a horizontal line through y equals 4. So it looks like this. I will sketch it, the function, for in green. So there it is. This is f of x equals 4. And we want to find the area under that curve, or in this case just a horizontal line, between x's 1 and 3. So let's sketch that. I'll use green again. So those are our 2 vertical lines, and this is the area that we want to find. Striped green here. Well, it looks like we do not need calculus to find this area. We just need geometry, and probably even before geometry you learned how to find the area of this rectangle here, just base times height. So our base here is 2 and our height is 4. Therefore the area here and this definite integral is just equal to 8. And that's as easy as that. Let's take a look at part B. Here we want to evaluate the definite integral from 0 to 3 of the function x plus 2. So let's sketch, again, this is just going to be a line, x plus 2, a linear function. I guess the previous one was also a line, that was a horizontal line specifically. This is a diagonal line, and it's going to have a slope of 1 and a y-intercept of 2. And we want to sketch it from x is 0 to x is 3. So if we start here at 2, we have a slope of positive 1, so we'll go up 1 over 1, up 1 over 1, and up 1 over 1. And I'm ending at the y value of 5, it looks like. So if I plugged in 3 here, I would get an output of 5, so that's correct. So this is our line. That's our function, f of x equals x plus 2. Then this integral represents the area underneath our function f of x from the line x equals 0 to the other vertical line x equals 3. So sketching that, here's the line x equals 0, here's the line x equals 3, and the area that we want to find under here is right there, now shaded in blue. So that is what this definite integral represents, is this area. Now this is a trapezoid, or you can think about it as 2 shapes put together, just a rectangle. So if you follow my pen here, this rectangle here, plus this triangle up here. You can think about it in 2 different ways. I say that just because a lot of students from teaching calculus previously, they do not remember how to find the area of a trapezoid, but I am going to just reteach that to you. So since we have a trapezoid here, the area of a trapezoid, so we'll write area of a trapezoid, is 1/2 the height of the trapezoid times the sum of the 2 bases. So the 2 bases are actually the parallel lines. So this is actually a base and this is a base. So if you think about this trapezoid being on its side, it works better. The height is actually this distance here, the distance between the 2 bases. So our height here is actually 3, and this base is a length of 2, and this base is a length of 5. So when we evaluate here after plugging this stuff in, we'll have 3/2 times 7, which is 21/2, or 10.5. So the area underneath the curve x plus 2 from 0 to 3, or the definite integral, is equal to 21 over 2, or 10.5. Again, if the area of a trapezoid was difficult to follow, it's just a rectangle plus the area of a triangle. Yes, you should know these area formulas from geometry, so at this point, if you do not remember how to find the area of a rectangle, a triangle, or a trapezoid, make sure that you figure it out and write it down, because we will be utilizing those three. Let's take a look at part C. This one is a little bit probably harder to know exactly what it is. This is actually a semicircle. If you recall, the area of a circle centered at the origin is simply x squared plus y squared equals radius squared. And that is just the equation of a circle centered at the origin, 0, 0. If we solve for this for y to get f of x equals or y equals, we'd have y squared equals r squared minus x squared. And then taking the square root, we'd have y equals the square root of r squared minus x squared. So we clearly have that here. This is just the top part of the circle, just because it's not plus or minus, it's only plus. So this is a semicircle, the positive part of it, and we can see here the radius would be 2, since this is 2 squared. Anyway, so it looks something like this. Between -2 and +2, a circle, only the top half of it, so a semicircle with a radius of 2 centered at the origin, would be out here, up to here, and over here, looking just like this. That's not half bad. So our area underneath that, down to the x-axis, is shaded here. And in order to find the area of a semicircle, we realize that since a semicircle is just half of a circle, it's just half of pi r squared. So our area of our semicircle is going to equal half pi times radius squared, since it's half of a circle's area, which is pi r squared. So our radius is 2, therefore r squared would be 4. So we'll have 1/2 pi times 4, and then half of that 4 ends up being 2. So we end up having the area equaling 2 pi. So this definite integral from -2 to 2 of the function the square root of 4 minus x squared times dx is 2 pi. If we take a look at A, B, and C now, we have found 3 definite integrals using only geometry and not really needing to use calculus. I suppose we did have to understand what the calculus notation was, but my point is that we're able to find area of under certain functions. If they form a geometric shape, we're able to find the area using geometry only and not calculus, using that long limit definition that we've done previously. Let's take a look at part D. Let's go ahead and sketch what we have in part D. We have the function x squared plus 1 from 0 to 1. So this function is a parabola or a quadratic here, which forms a parabola, and it's up 1. So if we plugged in 0, we'll get 1, and if we plug in 1, we'll get 2, and we know that it's curved, so it looks something like this. That's our function, f of x equals x squared plus 1. And we want this from under the curve from 0 to 1. So we want this value here, the area of this region. Now we're not able to use geometry here because this is a curved shape. If this was a straight line, then it would be a trapezoid. And it really is close to a trapezoid. I mean, we could estimate this pretty well. But because this is not a geometric shape, because it is curved here, and it's not curved like the circle, it's a little bit different. So we are unable to not use calculus here. We would have to use calculus. And so that's what I just did. So I'm using the limit definition that we've learned previously, that the area underneath this is going to be the limit as n approaches infinity of the sum from I equals 1 to n of f of, and then I found c sub I, which is I over n, and I found delta x, which is 1 over n, 1 minus 0 over n, and c sub I in the same way. Then I went through and found our final answer, which is 4/3. So I did the function at I over n, which is just x squared plus 1. So we have this squared and then plus 1 times I over n. Now that plus 1, all I did was multiply the 1 over n through, use summation properties to turn it into 2 separate summations, pulled out the coefficients, replace the sum from 1 to n of I squared with what it equals using those properties, or formulas rather. Same thing with this one over here. Then invoking the limit, once I simplified, we ended up with 2 over 6. These both went to 0 plus 1. So we had 1/3 plus 1, which is 4/3. All right, so that is a long process, but one that we know. But that takes a very long time to use that limit definition. Very shortly, we will find a simpler way of evaluating a definite integral when we cannot use geometry. We will no longer have to use this entire limit process. We will find an easier way to do this much more quickly. So, moral of the story is if you can use geometry, then please do so. If you cannot, we do still need to, at this point, use this limit definition to find the area underneath a curve. The second part of our video is all about the properties of definite integrals. Now, so far, we have seen the two limits, be a and b, where a is the lower and b is the upper, and a is less than b because we're moving from left to right on the x-axis. Well, these are two special cases where either the two limits of integration equal one another, or where they're swapped. So where it goes b to a, and we are going to see how we can work with these two special cases. So we can clearly see that this right here has no area. If we are trying to evaluate some function from a to a, if this is a, we're not evaluating it anywhere. It is literally nothing. So the area from a to a would be 0. Then, if we have the a and b values swapped, we can see that we can put them in the correct order from a to b, but it's just the opposite. So the definite integral from b to a of f of x dx is equal to the opposite, or the negative definite integral from a to b f of x dx. Let's take a look at what this means. In part A, we want to evaluate the definite integral from pi to pi of sine of x dx. Because our upper and lower limits of integration are the same, by our property, this equals 0. Then in part B, we can see that we want to evaluate from 3 to 1, which doesn't really make sense. It's like going backwards. So we can use that second property to say that this is equal to the negative definite integral from 1 to 3 of 4 dx. Now, we found this previously in our video. We know that this is the equation y equals 4 from 1 to 3, which is just simply this rectangle under here. So we did this a little bit previously in the video. And we found that this value right here, without the negative in front, is equal to 8 because it's simply just the area of the rectangle formed. So, by this definition, this guy right here from 3 to 1, the integral from 3 to 1 of 4 dx equals negative this integral, where we found that this integral already was 8, so this guy right here would equal negative 8. Here is another property of definite integrals called the additive interval property. We see that so long as f is integrable, I'm going to try that one, if it's able to be integrated on 3 closed intervals determined by a, b, and c, then this looks a little bit nuts. Here's the main idea. We have some function from a to b, and c is in between a and b. Well, the overall integral from a to b can be broken up at c. We would call this part here the integral from a to c. We would call this part here the integral from c to b. And you can clearly see that if we added this area up and this area up, it would equal the total area under the curve. This one seems kind of weird, like why would we even say this? Well, we might have some piecewise function, or we might have a function that can sort of be broken up at an opportune spot in order to use geometry maybe to find two separate areas. Let's take a look at this example here down in green and see why this would make sense to use this additive interval property. We want to let f of x be the absolute value of x, which again forms just a v for value. We want to find the definite integral from -2 to 1 of our function, the absolute value of x dx. So let's sketch this. and we want to go from -2 to +1, and our function, the absolute value of x, looks just like this, and it forms a V. And to the left of the y-axis here, when x is negative, it is simply just the line y equals -x, and over here to the right, it's just the line y equals x. So we can separate the absolute value of x into two separate linear functions. Then we want to find the area underneath this curve from -2 over to 1. So we can see that it's already sort of separated itself, and that opportune C value in the middle looks like 0. So we have one area over here and one area over here that make this total area. So we can split this up as follows. We can split it up just like this. Now, why did this function change on the inside? I could have kept it as the absolute value of x in each one of these, but I just want to show that the absolute value of x is defined as the line y equals -x when x is less than 0, and it's defined as y equals +x, a line with a positive slope, to the right of x equals 0. Again, I did not have to change these, really, because we're not really using them to find the area. We can clearly see that we can use geometry and the area of triangles to find the area of each one of these. So this one here will be this triangle right here, from x is -2 to x is 0. Let's find this area using geometry. So this triangle right here, it has a base of 2 and a height of 2, and in order to find the area of this triangle, it's 1/2 base times height. So we'll have 1/2 times 2, which is 1 times 2, so that area there is just 2. Then let's find this guy right here, which is the area of this triangle here from 0 to 1, and we'll do that one in orange. So this triangle obviously is smaller. The area of this triangle, again, is 1/2 base times height. The base here is 1 and the height here is 1. So this will end up having 1/2 times 1, which is 1/2 times another 1. So this has an area of 1/2. So our original definite integral from -2 to 1 was split up at an opportune spot, and we just see that we can just add this area plus this area to get the total area. That's essentially the idea of this added interval property. So our final answer is 2 plus 1/2, which is 2.5 or 5/2. These next two properties here of definite integrals might look similar because we've seen them in a very similar way being applied to our summation or our sigma notation. That is because definite integrals really are just sums of rectangles. So definite integrals really are just summation. So we can have these same types of properties. The first property says that if we have some constant k out in front of our function, we can pull that constant out in front and just deal with a simpler version of f of x on the inside. Then number 2 says that if we have the definite integral of two functions either being added or subtracted from each other, and functions again can just be terms. So if we have a couple terms, it can be more than 2 even, and they're separated by plus or minus, then we can simply separate our integrals using the proper either plus or minus depending on what was there. So this really allows us to simplify what we're working with. Let's take a look at an example. In this example, we want to evaluate the definite integral from 1 to 3 of the following function. Then we're given some values already. We're given the definite integral from 1 to 3 of x squared is 26/3. The definite integral from 1 to 3 of x is 4. And the definite integral from 1 to 3 of 1 dx is just 2. Let's rewrite this using these properties. So what I have done is I have rewritten the original integral that we want to solve using that second property that says that we can split up each term into a separate integral. So I've done that. The first term has its own integral. The second term, 4x, has its own integral. And I actually forgot to write the limits here. They should all have the same limits from 1 to 3. Lastly, this -3, I took the minus sign out front. I could have also had plus and then had a -3 in here, just depending on how you want to deal with negatives. So I split that up using our second property. Now we can use the first property that says if there's some coefficient in front, we can actually move it out in front of our integral. So for our first integral, we have a negative out in front. And so we can bring that -1 out in front. In our second integral, the 4 can come out in front. And in our third integral, the whole -3, or just the 3, since we already had the minus sign, can come out in front, and we just have 1 dx, or just dx. Now the reason that this is important is because look at the information that we're given. We are given what this equals right here, the definite integral from 1 to 3 of x squared dx. That's what we have here now that the negative's out front. Same with right here. We know the definite integral from 1 to 3 of x dx is 4. And that's what we have right here after pulling the 4 out front. Same idea here. So let's replace things with what we know. So what I have here is I sort of broke things up into different colors. So we have this integral right here is equal to 26/3, and then we have a negative out in front. So this is equal to -26/3. Our next one, we have a +4 times what this integral is equal to. It is equal to 4, so we'll replace it with 4. Then lastly, we have -3 times our final integral. This final integral from 1 to 3 of 1 dx is equal to 2, so we'll replace that with 2. And then we can simply just use algebra here to simplify. So using some algebra here, we end up getting our answer being 4/3. That in no way was planned to be the same answer as something previous we got in this video, but this is just sort of using the properties. It sort of seems silly to do it like this, but this example is just so you can practice these properties of definite integrals. Our last property is called the preservation of inequality property. And this is telling us that so long as f is able to be integrated, so if f is continuous and also non-negative on this closed interval from a to b, then our area underneath the curve, the definite integral, has to be greater than or equal to 0. That just means that we have to have some area underneath the curve. The area has to be a positive value or 0 if f was just the function 0. Then the second property tells us that if f of x is less than g of x, meaning if it's like lower down, if its y values are less than the y values of g for all x's from a to b. So this is one example of it. F is literally lower or less than g from a to b. Then the value of the definite integral from a to b of f of x is less than that of the value of the definite integral from a to b of g of x. And that makes sense. This is the area underneath the curve of f of x. It's this area in here. Then this right here is the area under the curve of g of x down to the x-axis. It's literally more area because g of x is taller or has greater y values than f of x. Again, seems kind of obvious, but these are all sorts of things that we put as properties so we can write them out in a mathematical way and understand them in a more logical way.